Let's take a look at the mechanism now. How does this reaction occur? So first, remember our ylid structure, triphenylphosphine. We're going to draw the ylid form, and as you might imagine from drawing this as a carbon anion, it's very nucleophilic, and of course a carbonyl, and I'll illustrate it quite simply here with just acetone, is an electrophile, so we get formation of the carbon-carbon bond and opening up of that reaction. Now, this can be in equilibrium with what's called a betaine. So the phosphorus can expand its octet, so we can imagine that that could attack the phosphorus. After all, we've got to make those phosphorus-oxygen bonds. Now, sometimes, again, depending upon the details of the structure, the stability of these kinds of anions and forms, this can actually go straight here. And in some instances, the Wittig reaction can be reversible. So, for instance, there are ways to control cis and trans geometry through, again, discrete details that are beyond the undergraduate level and we're not going to worry about today. But once we have formed the betaine, then we can imagine this as a retrocyclization, a reverse 2 plus 2 cyclization, and if we follow those arrows, you see we'll have an oxygen phosphorus double bond, and we have formed the carbon double bond. Let me put these back in those positions. And so we make the double bond at exactly the same position where previously we had the CO double bond. And so that's the mechanism of the Wittig reaction. By the way, this was betaine, B-E-T-A-I-N-E, betaine. All right, the mechanism of the Wittig reaction.